All right, P.3 is going to continue our discussion of exponents, but it's going to change our exponents into something we haven't dealt with yet. Those are called rational exponents. Rational numbers, we mentioned last class period, they're things that are fractions and decimals. Okay, so we're talking about exponents now that are fractions or decimals. So as you look at this, what you might want to recall is some notation from radicals that will come into play. So our radical, like the nth root of a, or if there's nothing written, we understand it to be the square root of a. Those have other versions of how they can be written as exponents. When it's the nth root, it can be written as 1 over n. And when we're dealing with a square root, it can be written as a to the 1 over 2. So whatever the index is on the radical becomes the denominator of the fractional exponent. Why is that helpful? Well, it's actually helpful because it means that all those properties that we already established for exponents have a connection within radicals in the very same way, and we'll be able to use those. So a couple of them, for example, is what happens when we have the nth root of multiplication and the nth root of division. You will notice we do not have anything that has the nth root of addition or the nth root of subtraction. None of that happens at all, okay? It's just multiplication and division. So because this has this corresponding component, I'll show you one of them, where I can take the a to the n, I didn't write that, the ab to the 1 over n, like this. I can write it that way. And I can distribute that 1 over n power to each of them, like so, right? That's a property from exponents. But the exponent of 1 over n means it is the nth root of a and the nth root of b. So we almost get it for free because there is a rational exponent notation. We get all of the properties of exponents. So I'm going to write this, I'm going to shift this up so it's kind of out of our way. This is the property that we're going to be using. The nth root of a, b is the nth root of a, nth root of b. And in quite the same fashion, we can do the same thing when it's division. It's the nth root of a divided by the nth root of b. Okay. So much like in the last section, we're going to look at this and how it plays out with numbers involved. And we're going to look at this and see how it plays out with variables involved. They're very similar, but sometimes we get to actually like find the exponential value when we're dealing with numbers, whereas we don't get to do that with variables. A quick reminder too, I know I gave you notes for P1 and P2. If you want to get notes for the rest of everything, they're inside of Canvas, and you can go print out notes for P3 and P4 and all the rest of the semester, and so you won't have to write quite as much. Some days that's more important than others. So we're going to do some examples. This one actually is, they're starting out being written on 1 and 2 with the notation that has that rational exponent, right? It's got a rational exponent notation. And we're going to actually change them sometimes back into radicals and sometimes from radicals into rationals, depending on what we need to be able to simplify. So on this one, it's very nice to be able to change this into a radical notation, right? The power of 1/2 is a radical with an index 2 or a square root. And we have a property that says that we can square root each of them individually. What's the square root of 1? And the square root of 4? 2. Okay, so I'm going to reiterate this throughout the whole year. I mean, that's going to happen our semester. If you put into your calculator the 1/4 in parentheses and raise it to the power 1/2, it's going to give you the answer of 1/2. It's going to do that. And so you can confirm it, and I have no problem with you confirming with your calculator any answer you want. But you can't just do it with your calculator, because the whole point is that we're applying these properties sometimes with numbers, because that way when we apply them with variables, when our calculator is not usable, we are able to do it there too. So if you simply jump from here to here, you're not going to get a whole lot of credit, maybe none, on the problem, because what you did, most likely, is you do it in your calculator. And I didn't ask what your calculator knew how to do. I asked what you knew how to do. Okay? All right, the next one. Okay, do you remember when we're talking about exponents and we have negatives involved, if there's no parentheses that include the negative, then that negative is not part of the exponent, right? The exponent doesn't apply, right? So like that last one that you had asked me about, Tori, on the last one we did, and you were asking me about that negative in the front, it was in parentheses, right? And it was raised to the power 2, so we had to apply that power 2 to the negative. Here, there's no parentheses that include the negative, so it is irrelevant to the power. So in a very real sense, if you want to sort of put parentheses in to identify to yourself what the 1/2 does apply to, it's just to the numerical value, not the negative sign. So I've got the negative in front. The power 1/2 is a square root. And now you probably know what the square root of negative 144 is. It's 12. 12 times 12 is 144. We'll talk about breaking things down when they're less familiar because we'll get to it. But if you know the value immediately, that's great. Okay, so on number 3, we have a couple of different options. We can consolidate the y's first, right? We've got y on top, we've got y to the 1/2 on bottom. So we could do that first if you wish. Or we can distribute the 3 first. So what would you guys like to do? Distribute the 3. Okay. So if we distribute the 3, we want to remember that it applies to every piece that's in here. So there's 3 of them. So I have x to the 1/2, and I have to multiply the 1/2 times 3, so now it's x to the 3/2. Right? I just have y, so now it's y to the 1/2. And on bottom I have, I'm sorry, not y to the 1/2. I've got too much going on my screen. It's a 3, y cubed, so sorry. And on the bottom, the y to the 1/2 is raised to the power of 3, so now it's y to the 3/2, much like the x was. Is that part okay? So you're multiplying, even if it's fractions involved, you're multiplying the fraction by the power of 3 on the outside. So our directions here, I don't have them written down, but we've already worked through them, is that we're rewriting in simplified radical form. We didn't have to worry about it on the first couple because they actually ended up being integer values or fractional values. They didn't have any radicals still involved. But on this one, we have variables involved. There's no numbers to deal with for the bases. I do need to fix the fact that this is y cubed and y to the 3/2. So I'm going to use the property of exponents where I can subtract my exponents. So this is x to the 3/2 on top. And we have y to the 3 minus 3/2. In order to subtract fractions, they need to have the same denominator. So the 3 is the same as 6/2. So 6/2 minus 3/2 happens to be 3/2. So my exponent ends up being 3/2 on both of my variables. So I have x to the 3/2, y to the 3/2. Now if I were given the directions where I was allowed to leave them in rational exponent form, I'd be done. But I'm going to be changing them into radicals. And I chose this one on purpose because I want to show you something interesting that happens with this particular radical. This particular radical doesn't just have the index in. It also has an exponent on the variable that's inside. And that's something we haven't yet seen. So when we have that x to the 3/2, y to the 3/2, the index is 2, but the power on x is 3. So the 2 in the denominator down here comes out as the index, but the power 3 is still the power 3. Okay, and the same thing happens for the y. And I'll show you one other way we could write this in a moment, but I'm going to deal with it this way right now. Okay, so let's talk about simplifying a square root when I've got 3 values underneath. So in a very real sense, I have the square root of x, right, 3 x's. So 2 of these x's match the index of 2 on the outside. So when I take the square root of x squared, that x comes out. And the same thing happens with my y. There's 2 of them. So you'll notice I'm no longer writing the index 2. I don't have to. If you want to, you can. But there's an x and there's a y that come out. But there's also the x and the y that are still underneath. Let me shift this one more time. Do it this way. So there's an x still and a y underneath the radical here and here. And I put them back underneath the same radical because I can. They're both underneath the square root individually. And we had that property that said that we can separate them out individually. We can also consolidate them back together. So the doubling of the x's underneath came out as 1x. The doubling of the y's came out as 1y because it was a square root. The single x and the single y that didn't have a pair stayed there. So this is the simplified radical form of the original expression. Okay? That one's weird. Okay, let's do some more with some numerical values. Okay, so as we're taking a look at a few of these, I want us to get a little bit more comfortable with the idea of looking for pairs of things or groups of threes of things. So this is a really good example, number 4. I've got a cube root this time instead of a square root. And some of you may be really comfortable with the cubed values, like you know what 1 cubed and 2 cubed and 3 cubed and 4 cubed are, and because you just like, numbers are kind of that way in your brain. Some of you may not be, and so I kind of want to speak to that for just a moment if that's you. So particularly the number 125 is getting a little bit larger. We've seen it earlier today. But if you didn't know what to do with 125 and you were simply breaking it down into its factored forms, okay, its factored form, what we would ask ourselves is, what does 125 divide by? Anything. 5. All right, so it's 5. And if I divide 125 by 5, I get 25. 5's prime, so I'm stopped on that particular branch of my tree diagram. Over here, 25 breaks down into another 5 and 5. So I'd like for you to take a look at this kind of from the perspective of the last problem we did. I actually now have 3 5s on top. Okay? 8 happens to work much the same. If I break 8 down, I've got 4 and 2. 4 is 2 and 2. So it's actually 3 2s on bottom. Because it's a cube root, I'm looking for groups of 3. Okay? The last problem I was dealing with a square root, so I was looking for groups of 2. If I had a 5th root, I would be looking for groups of 5. Right? So whatever the index is on the outside, that's how many have to be in my group to be able to simplify anything. So there are 3 5s here, which means a 5 can come out. There are 3 2s here. Oh, no wonder you guys are looking at my screen like I've lost my mind. I don't know why there's a 3 there. Let's fix it. How about a 2? That's better. There are 3 2s here, or there should have been. So there's a 2 that comes out. There is still something I haven't dealt with. Does anybody know what it is? It's the negative. So interestingly enough, you probably remember that somewhere along the way that somebody said, well, you can't take a square root of a negative number. Do you guys remember that? At least that they did that until you encountered things like the number I. And then there was this weird nuance to that, and we'll talk about that in about a week and a half. But there was a square root issue with negatives. Those issues don't happen with cube roots. In particular, they happen only with even roots versus odd roots. 3 is an odd number. So the cube root of a negative number is actually negative, but I can show you exactly why. On the top, we wrote down that the 125 was 5 times 5 times 5, right? And then there's a negative in front. But it would be also true that negative 5 times negative 5 times negative 5 is also negative 125, right? Because odd numbers of negatives stay negative. Even numbers of negatives change to positive. So that's why I'm actually able to pull the negative out when it's an odd index, which this one was. If there had been an even index, there would not be a real solution to this. It'd be imaginary, again, which we'll talk about later. But the negative does come out because it's an index that's odd. Okay, so on number 5, what you notice is that there's a negative, right? But the 3/4 exponent is unattached from that negative, yeah? Now, we've seen this happen a lot of times, so I hope that's sort of sounding like, could she stop saying that? I got it. I got it last class period or sometime today, I don't know. But that negative is staying negative because the exponent has nothing to do with it. There's no parentheses around it. So the negative stays negative. When we rewrite this in simplified or in exponential form, in radical form, the 4 as the denominator here comes out as the index. And the cubed stays inside with the 2. That's simply rewriting the form. Here's the problem. It's not really a problem, but here's the difference maybe with this and the previous problems. Is that 2 cubed is 2 times 2 times 2. But my index is a 4, which means that in order to pull anything from the inside to the outside, I'm looking for a group of 4. And this is only a group of 3. There's only 3 2s, right? So I can't actually pull anything out. The only thing that's left for me to be able to do to write it any better than it is right now is to simply write this as an 8, because 2 times 2 times 2 is 8. I can't pull anything out. All right, on number 4, it's got a 4 in it, number 6, this is simply an example that I wanted to show you how we can change to exponential form. Okay? This is actually quite a bit like where that last problem, number 5, ended. I have 2 x's underneath. I have an index of 3. I can't pull anything out. So those direction sets, it doesn't make sense. So this is actually a different direction set that I'm showing you another example for. But I'm just having us rewrite it in the other way. So the 4 in the front stays in the front. The x to the power 2 is still to the power 2. When I'm rewriting this in the other form, what will happen to the 3 in the part of the cube root? It'll be the denominator of the 2, right. So I will have a denominator 3 for the 2, and this is the exponential form that this would be written in. So different problems are going to have some little bit different directions on them, and that problem would have something like that. It would want you to write it in exponential form. Okay, we're looking at a few more problems that have exponential simplification, radical simplification. I don't want to use the word exponential there, radical. Okay, so the index is 3, so I'm looking for groups of 3 items, right? Groups of 3. We've talked about the negative. Because the index is 3 and it's odd, what's going to happen to the negative? It's going to stay negative, but it's going to come on the outside. All right? So I get to pull it out almost like for free because I have an odd index and it's negative, so the negative is going to come out. So the next thing let's do is let's actually look at the number 24. So somebody tell me something I could divide 24 by. 6. It'd be 6 and 4. And then 6 divides into 2 and 3, and 4 is 2 and 2. So I actually have 1, 2, 3 2s, and a 3. That's the number 24. And I have how many x's? 5. Or a's. Is it a's? What's my letter? A's. 5. 1, 2, 3, 4, 5. So when I say things that sound silly and you're like, can't she just see it? It's because my screen is zoomed in and I actually can't. So that's what happens when those things happen and you're like, what is she thinking? Okay. All right. So I'm looking for groups of 3. So I have 3 2's. That's cool. What else do I have 3 things of? A's. So I don't have all the A's, right? I can only circle 3 of them, but 3 of them are a group of 3. So I'm going to be able to take one of the 2's, or pull the 2 cubed out as 1 2, pull the A cubed out as 1A, and the negative that's on the outside is still there. So I have the same negative, and I have a 2, and I have an A. But I have a cube root of still some stuff that's underneath the radical that did not get to come out. What's still under there? A 3 and 2 A's, which is A squared. So we end up with this as our simplified radical form. Okay. Yes, ma'am.
So like just on number 7, like just to clarify, it was like to the, if like 3 was a 4, it wouldn't, the negative would like change.
You're right. So if I had a question like this one, and instead of it saying the cube root, it said the 4th root, the negative that's underneath the radical would stay under the radical. It would not be able to be pulled out. We'll talk about what happens with that negative when we get to P.7, when there's an index that's even.
But we don't have anything on
Don't think that you'll have anything on your homework that's trying to sort of trick you on that. That's not the point yet. We will end up with negatives underneath radicals, but not till P7 for indexes that are even. Okay, on number 8, what students really want to do is they want to use the properties of radicals that are for multiplication and division, and they want to use them for addition and subtraction. That's what they'd really like to do. They'd like to put a radical and simply say, okay, we're going to do 18 minus 50 plus 12 minus 75, put it all underneath the same radical. That's what people really would like to do. And I'd like to give you a simple example of why it doesn't work, because I don't think that just telling you that it doesn't work is going to stick. So I'm hoping if I show you an example of why it doesn't work, then it might actually stick. We're going to look at the square root of 9 and the square root of 16. So if this actually worked, and you could simply do the square root of 9 plus 16. 9 plus 16 is 25. And what's the square root of 25? 5. So if I were able to mush them all underneath the radical, I would get the answer of 5. But what is the square root of 9? And what is the square root of 16?
4.
And 3 plus 4 is most definitely not 5, right? So it is absolutely not true that I can simply push them all underneath the same radical. I can't do that. I will not get the same value. So the best and only thing I'm left with doing is individually looking at each one of these radicals and factoring them much like I did the 24 above. Now, sometimes you see the factors very quickly. There's no reason to do any trees or scratch paper or anything, and that's great. Sometimes it's not as easy. So I'm going to write them down just where they are as their factored form. And if you don't need to write them to see their factored form, then just don't. That's fine. So 18, what divides 18? 2 and 9 would be 3 and 3. What divides 50? 5 and 10. 5's prime, so 10 becomes 2 and 5. How about 12? 3 and 4, 4 and 3. 3's prime, 4 is 2 and 2. 75. 3 and 25, and 25 is 5 and 5. Okay, good job factoring. So I'm going to write each of these underneath the radical like I did on number 7. If you don't want to write them underneath the radical, you don't have to. You could do it from this view, and that's still okay. So I'm going to write them just in case you need to see them that way to see what's happening. I have 2 times 3 times 3. Subtraction. I have 5 times 2 times 5. Actually, I'm just going to write them grouped together, the ones that match. 5 times 5 and then the 2. We have 2 times 2 times 3. And then we have 3 times 5 times 5. Is everybody good with that so far? So if you've actually decided to write this out, you're going to look for those groups of 2. Why is it groups of 2? Because it's a square root, right? So each one of them happens to have a group of 2. If you want to use the factored notation you did up here, you could do the same thing. There's a group of 2. Here's a group of 2. There's a group of 2. Here's, whoops, that's not it. There's the group of 2. So you could do it from there. It would work just fine. And we need to bring out the groups of 2 a single time. So the 3 squared, the double 3's underneath come out as a 3. So this is 3 square root 2. 5 square root 2. 2 square root 3. And 5 square root 3. So that is individually simplifying every radical. But some of these radicals now are like or alike terms, right? They're alike or they're like terms. So anytime we have the same, this is called a radicand, the number underneath. Anytime we have the same index, which we do, they're all square roots, and we have the same radicand, and some of these are the same radicand, we can combine them. So these two are like terms because they're both square root 2's. So I have 3 square roots of 2 minus 5 square roots of 2. What's 3 minus 5? Negative 2. So I have negative 2 square roots of 2. And then on the other one, I have square root 3's, right? I have 2 square roots of 3 minus 5 square roots of 3, which would give me negative 3 square roots of 3. Why can't I not combine those two together? They have different radicands. Same indexes, right? They're both square roots, but one of them is square root of 2 and one of them is square root of 3. So I can't combine any further, so I'm stopped at that point. All right. We have just like 3 more, I think. Number 9 brings us back to the idea of exponents that we had dealt with before. When we looked at exponents in section P.2, we talked about being very careful that if we have a parenthesis raised to a power like this one, that exponent distributes to everything inside, including coefficients, including exponents that are already there, including signs that happen. And so we want to remember that those things apply to radicals. So as I deal with this squaring here, I would have to distribute to both pieces. I'm going to show you one other way to think about this, but this is one of them that relates back to what we did before. So I have 3 squared now, and I have square root 5 squared. So what is 3 squared? 9. And what is the square root of 5 squared? It would be the square root of 25, but that has another form. 5. Yeah. So the square and the square root eliminate one another. They're inverse operations. And then 9 times 5 is 45. So this is one way to think about it. Another way to think about it, because the exponent is just a square root, you could think about it as simply multiplying the values by themselves. This is 3 square root 5 times 3 square root 5. So you've got the 3 times the 3 here. You've got the square root of 5 times the square root of 5 here. And of course, you'll end up with the same solution. But it's thinking about it more from the definition of what exponents do instead of what properties of exponents you have at your disposal. Either one's probably the same length of time it takes you to do the problem. All right, so on number 10, there is a slightly different direction because we haven't seen an example of this yet. The directions talk about rationalizing the denominator. So I will tell you right now that I find rationalizing the denominator to be a little bit annoying. And the reason that I do is because I feel like it might be one of those things that in the next 10 years or so you see them just moving out of textbooks completely because it's really just not something that's necessary with the technologies and things we have these days. But it's still there for the moment, and it's not particularly difficult to do. It's just annoying, okay? So what it means to rationalize the denominator is that you don't have radicals on the denominator when you're done. So right now there's a square root of b in the denominator. I don't want the square root there. How do I get rid of it? Well, what I can't do is I can't square the denominator. Because squaring the denominator and squaring the numerator are not the same thing. Right? I'm allowed to do the top to what I'm doing to the bottom with multiplication, not with squaring. But what I can do instead is I can multiply by the denominator. So what I really want is I want the denominator squared. But instead of writing it squared, I'll just write it times itself. So the square root of b is multiplied by the square root of b, but whatever I do to the denominator, I have to do to the numerator, right? So I'm not squaring, but I'm multiplying it by the square root of b. Now, the beautiful thing that happens in the denominator is exactly what happened right here on the problem above with my square root 5 squared, right? When you square a square root, or when you multiply the square root by itself, those operations eliminate one another. So the square root of b times the square root of b is b. And lo and behold, there's no radical in the denominator anymore. But what you gained with no radical in the denominator, you now lost because you have a radical in the numerator, which is why I say it's a little annoying. And I don't really think that you could probably use the word simplify and say that this is simpler than what we started with. It looks more complicated. But there are components in further math classes where having a rational number in the denominator is preferable for different reasons. So that's why we see it still in play to some extent even now. It's not hard, but it's annoying. All right, the last one, number 11, is kind of interesting. So I'm going to show you how it works, and then I'm going to show you that you actually have the ability to do it in a shortcut way, okay? So according to what we know about rational exponents, we have two indexes here, right? There's an index of 4, and then there's an index on the outside of 3. So we can actually rewrite this 2a to the power of 1/4, all to the power of 1/3. That's the definition, the exchange that we can make into this other form. So what do we do with the exponent raised to the exponent? We multiply the two exponents. That's a property we have of exponents. Fantastic. So now I have my 2a, and I have the 1/4 times the 1/3, which is 1/12. And then I can put it back in that radical form then with an index of the 12th root of 2a, depending on what your directions say. So what does that mean you really have the ability to do? Well, it really means that you have the ability to multiply indexes when there's multiplication underneath, right? A little different when there's other things, but multiplication or division this works for. So I could actually come straight down here to the fact that this is the 12th root of 2a. All right, so we're done with P2 and P3. So let's chat for a second, and I'll keep the video recording going just in case someone from our class is watching later. Homework for P2 and P3 are both due on Thursday. Hate it when there's two homeworks between a Tuesday and a Thursday. I hate it for you because it's a lot, and I recognize that. So you're probably looking at a considerable amount of problems because you've got 2 sections worth between now and Thursday. The Success Center is available to you. My office hours are available to you if you're stuck, okay? I'm definitely going to collect at least one of these 2 assignments on Thursday. So you really do need to complete them to the best of your ability. I would love to be able to tell you, come with questions to class on Thursday, but I honestly cannot do that. And the reason I cannot do that is because we don't have time to do questions and still keep moving forward. College Algebra is one of these classes that I struggle every time I teach it to stay on track with the syllabus. I struggle because there's so much material. Now, you will bring one of those assignments to class you'll bring both of them to class on Thursday, all right? Also on Thursday, if you take a look back at your schedule, we're having a quiz, okay? The quiz will be over sections P1, P2, and P3. If I remember right, it's 3 questions, 1 from each section. It's not a long quiz, but that is what we will start with. So the first 15-ish minutes of class, we will be taking a quiz. So first you'll come in, you'll turn in whatever assignment or assignments that I collect, and I'll show you how we turn those in. You'll do it like in real copy, so you need to have a paper copy. So those of you who've maybe done some of these things electronically on a tablet or something with your homework, that's fine, but you gotta have it printed off for me, okay? So you're gonna bring those, and then we're gonna take a quiz, second, and then we will move on into section P4 and P5. Hopefully we finish both of them. We'll just see how that works out with the quiz in there too, okay? So we're ending just a touch early today because starting now would be silly. Have a lovely day, and I'll see you guys on Thursday.